Hi, this is Tzvi Rosen with another lecture on matrix theory, and today we'll talk about diagonalization. In the last lecture, we learned about eigenvalues and eigenvectors, and these are associated to a square matrix A. So if we have A, an n by n matrix, okay, then an eigenvalue is a value lambda. This is usually a real number. In some contexts, a complex number, but we'll take it to be a real number. And V is a vector in Rn, satisfying the following relationship: AV equals lambda V. Okay, so this vector is called an eigenvector. And of A, and this is an eigenvalue of A. Okay, and these are special because A is acting on this vector as a contraction or dilation on that vector. So it's just stretching it. It's not changing its direction at all, just stretching. On V by scaling. Okay, so let's consider a nice situation where the standard basis vectors are all eigenvectors. So in this example, let's stick with R3. Okay, suppose, for instance, E1 is an eigenvector with associated lambda 1 equals 3. E2 is an eigenvector with lambda 2 equal to minus 1. And E3 is an eigenvector with lambda 3 equal to, let's make it 0. Okay, so then what does the, and this is all for some matrix A. Okay. Matrix, this will be a 3 by 3 matrix A. Okay, so what does A look like? Well, we know that you can write the matrix explicitly by writing AE1, AE2, and AE3. And we know that AE1, it's just scaling it by 3. So it'll give back 3 and 0, 0 because you don't get any copies of E2 or E3. How does it act on E2? Well, it just scales E2 by minus 1. So we'll put that in there and you get no E1 or E3. And finally, you have E3 with eigenvalue 0. So when you plug in E3, it gets scaled to 0. So you get 0 back. So it's a 0 column. But what we see in particular is that we have a diagonal matrix here. Okay, and meaning that the only non-zero values are on the diagonal. And that's because we're working in a basis of eigenvectors, right? So the only thing that happens to any of these eigenvectors when you apply the matrix is scaling. And that's why we have everything on the diagonal, because you're just scaling each basis vector. Okay. But what if some other basis vectors are eigenvectors? So we have a let's say we have a basis of eigenvectors, but they're not just the standard basis vectors. So for instance, let's do an example where we have R2, and we're going to take 1, 1 to be one eigenvector, and let's call this V1, and V2 will be 1 minus 1. Okay, and let's say that, so we have A is a 2 by 2 matrix, and let's say that lambda 1 is going to be 2, and lambda 2 is going to be minus 1. So if I know what the vector looks like in this basis v1, v2, I can just apply the matrix A in a straightforward way. So let's say I have A applied to v1. Well, I know v1 is an eigenvector, so that's going to be it's an eigenvector with eigenvalue lambda 1, so that's going to be 2v1. Okay, or if I have A v2, that's going to be minus v2. Okay, what if I have something like A 3v1 plus 4v2? Okay, well then that's going to be 3 times A of v1 plus 4 times A of v2, and this is by linearity. You can always distribute A to a linear combination of vectors. So this is going to be equal to 3 times 2v1 plus 4 times minus v2, or 6v1 minus 4v2. Okay. But in general, it's going to be tricky. So if I just have some arbitrary vector, let's say, let's say the first basis vector, 1, 0. So what I would have to do, this is our E1, so what I have to do is translate it into coordinates relative to this new basis. And let's call the new basis B prime. And then apply the matrix A. So in particular, with 1, 0, I could tell that this is equal to a half of 1, 1 plus a half of 1 minus 1, okay, which is just a half of v1 plus a half of v2, and that's going to end up being, so when I apply A to this, so A times a half of v1 plus a half of v2 is going to be 1/2 times 2v1 plus 1/2 times minus v2, which is equal to v1 minus a half of v2. And plugging in our value for v1 and v2, we get that this will be equal to 1 minus 1/2 minus a half, which gives us 1/2 3/2. Okay, so that's a way to get the value of A on this vector, but it involves translating into a different set of coordinates. So what we would really love to do is to phrase A as a combination of operations like change basis to B prime. Okay, that's going to be the first thing you do to your vector. Then apply A, or apply the scaling from A, using the eigenvalues, and then change back to original basis. Okay, which is basically what we did here. Okay. And so what we're going to do in order to do this is define similar matrices. So two matrices, so let A and B be n by n matrices. Then A and B are said to be similar if there exists an invertible matrix. Exists an invertible matrix P such that A equals P, B, P inverse, or equivalently AP equals PB. These are the same thing. Okay, so let's take a quick example. If I have the matrix P equals 0, 1, 1, 0, P is its own inverse, so this is equal to P inverse. So any matrix I take, so if I have, let's say, A equals 1, 2, 3, 4, and then I take PA, P inverse, so this would be 0, 1, 1, 0, 1, 2, 3, 4, 0, 1, 1, 0. This will you can do the multiplication in whichever order you want. So let's first do this. We get 3, 4, 1, 2, and then when we combine that with 0, 1, 1, 0, we get 4, 3, 2, 1. So what that tells me is this, if I name this matrix B, then these two matrices, A and B, are similar because there's a matrix P such that B is equal to PAP inverse. Okay? Cool. So now we get to diagonalization. And diagonalization takes square matrix A, a square matrix whose eigenvectors are a basis for the vector space. So let's say it's an n by n square matrix, then its eigenvectors are a basis for Rn. Okay, and you have to be a little careful about that, because if you don't have a basis, then you're not going to be able to diagonalize. Then we can write P equal V1 through Vn with the eigenvectors as columns. And then the matrix A can be written as P inverse D P, where, sorry, it should be P D P inverse, where P is as above and D is equal to lambda 1 down through lambda n, okay, being the eigenvalues. Okay, and this might be kind of shocking. Why should I be able to factor a matrix in this weird way using the eigenvectors and eigenvalues? But when you think about it in the way we just described with the changing basis and scaling, this makes perfect sense. First, you change from the standard basis to the eigenvector basis. That's what P inverse does. Then you apply the eigenvalues, because you're just scaling each of these axes, and then you switch back to your original basis. So that's really what A is all about. And that's what the diagonalization is all about. This factorization is called a diagonalization of A. Okay. So let's see this in action. We start with this matrix 2 by 2, 6 minus 1, 2, 3. And the first step is to find the eigenvalues and eigenvectors. Okay, So let's recall how to do that. We take determinant of a minus lambda I, which is equal to the determinant 6 minus lambda, 2 minus 1, 3 minus lambda. This is equal to 6 minus lambda, 3 minus lambda, plus 2, or lambda squared minus 9 lambda, and plus 18 plus 2 is plus 20, which gives us lambda minus 4, lambda minus 5 when you factor. Okay? So we have these two eigenvalues. Our eigenvalues are lambda 1 equals 4 and lambda 2 equals 5. Okay, next up, we find the eigenvectors. So plugging in lambda 1, we get 6 minus 4 is 2, minus 1, 2, and minus 1. Okay, so this is the same row. So if I have x1, x2 here, what this tells me is 2x1 minus x2. So this should be equal to the 0 vector, which implies 2x1 minus x2 equals 0, or our eigenvector x1, our eigenvector, let's call it v1, will be equal to 1, 2. Okay, or any scaling of that, but that's any non-zero scaling of that. So that's our first eigenvector. If we plug in lambda 2, which was 5, then we get 6 minus 5 is 1, minus 1, and 2 and 3 minus 5 is minus 2, times x1, x2. This is equal to the 0 vector, which means that x1 equals x2, and the associated eigenvector is 1, 1. Okay. So we have our two eigenvectors and our two eigenvalues. So we know that our matrix D is going to be the one with the eigenvalues on the diagonal. That's 4, 5. And our matrix P is going to be 1 minus, should be the two eigenvectors in a row, 1, 2, and 1, 1. This corresponds to eigenvector v1, and this one corresponds to eigenvector v2. Okay, and now the next step is to compute P inverse. Okay, so P inverse is the inverse of 1, 2, 1, 1. Okay, and with 2 by 2 matrices, we have a formula that we can use. It's going to be, this is inverse, it's going to be 1 over the determinant, which is minus 1, times, I think we swap these elements and we negate these elements. Okay, so that the answer at the end is minus 1, 1, 2, minus 1. Okay. So that tells us that our original matrix A should be equal to P, D, P inverse, which in our case means that 6 minus 1, 2, 3 is going to be equal to minus 1, P is first, so it's 1, 2, 1, 1. And then the diagonal matrix was 4, 5. And the inverse is minus 1, 2, 1, minus 1. Okay? And you can, why don't we double check that this truly gives us the we are going to go to the next page. Oops. And just confirm that this equation holds. So let's combine these two matrices first. Okay, so we get 4, 5, 8, 5, and then times this matrix -1, 1, 2, -1. And together these two give us 4 times -1 plus 5 times 2 is 6. 4 times 1 minus 5 times 1 is -1. 8 times -1 plus 10 is 2. And 8 minus 5 is 3. And indeed, these two are equal. So we just found a way to write our matrix factored as a diagonal matrix and then with a P and a P inverse, just using the eigenvectors and eigenvalues. Okay, let's do it for a little bit of a harder example, 3 by 3. And we've seen this matrix in a previous lecture, but we'll do the eigenvalues and eigenvectors again. So to get the eigenvalues and eigenvectors, we start by taking the determinant of A minus lambda I. This is 1 minus lambda, 2, 1, 6 minus 1, 0. Sorry, 6 minus 1 minus lambda, -1 minus 2 minus 1. And we get this as, we'll take it across the middle row, so it's -6 times 2, 1, sorry, this should be -1 minus lambda, 2, 1, minus 2, minus 1 minus lambda, plus -1 minus lambda times 1 minus lambda, 1, minus 1, minus 1 minus lambda. This is equal to -6 times -2 minus 2 lambda plus 2 plus -1 minus lambda times -1 plus lambda squared plus 1. This is equal to 12 lambda. We have lambda squared minus lambda squared times 1 plus lambda, which gives us lambda cubed minus lambda squared plus 12 lambda. Actually, minus lambda cubed plus lambda squared minus lambda squared, which should be equal to, which is, we can factor out a minus lambda here to get lambda squared plus lambda minus 12. And this has its factors, so minus lambda, lambda plus 4, lambda minus 3. Okay, and that factors that quadratic. Okay, so this means that the eigenvalues are lambda 1 equals 0, lambda 2 equals 3, and lambda 3 equals -4. Okay, that's step 1, is eigenvalues. Now let's get the corresponding eigenvectors. Okay, so we'll start with lambda 1 equals 0. So here we want to find the kernel of A minus lambda I, which is just A. So we'll see 1, 2, 1, 6 minus 1, 0, minus 1, minus 2, minus 1. So this, well, the first row added to the third row gives, these are opposite, so we definitely get that cleared. So we have 6. You know what, while we're at it, let's add minus 6 times row 1 to row 2. So we get 0 here. This is minus 13 and minus 6. And these are zeros. Okay. And what this gives us is, well, we can, let's do Gauss-Jordan. Let's eliminate above the minus 13. So we can first do minus 1 over 13 times row 2, which gives 1, 2, 1, 0, 1, 6 over 13, 0, 0, 0. And then we can add minus 2 times row 2 to row 1 to get 1, 0, 1 over 13, 0, 1, 6 over 13, 0, 0, 0. Okay, and what this means is that we have a one-dimensional kernel. We have one vector in the kernel of this matrix, which can be given by x1 minus 1 over, plus 1 over 13 x3 equals 0, and x2 plus 6 over 13 x3 equals 0. So taking x3 equal to 13, for simplicity, that means x1 is minus 1 and x2 is minus 6. So we have v1 equals minus 1 minus 6, 13. Okay. Okay, our second eigenvalue was either positive 3 or negative 3. It was positive 3. So if we take lambda 2 equals 3, what do we get? Well, it's minus 2, minus 4, and minus 4 on the diagonal, and then everything else stays as it is. Okay, and we can now do row reduction to compute the kernel. So we'll take 3 times row 1 and add it to row 2, and we'll take minus a half of row 1 and add it to row 3. And what we get is minus 2, 2, 1, 0, 2, 3, 0, minus 3, and minus 9 halves. Okay, and let's scale this by minus a half, and we'll scale this by positive a half, and get minus 1, 1, minus, sorry, this should be positive 1, minus 1, minus 1 half, 0, 1, and 3 halves, and 0, minus 3, and minus 9 halves. Let's add 3 times row 2 to row 3, and we'll also add row 2 to row 1 to get rid of that minus 1 above, and we get 1, 0, 1, 0, 1, 3 halves, 0, 0, 0. Okay, and we expected this. And this gives us the equations x1 plus x3 equals 0 and x2 plus 3 halves x3 equals 0. So we'll set x3 to be 2, and then x1 is going to be minus 2, and x2 is going to be minus 3. Okay, so our eigenvector is going to be minus 2, minus 3, 2. Okay, and finally, lambda 3 equals 0, sorry, lambda 3 equals minus 4, I believe, and plugging that in, we have a minus lambda I is minus 3, 2, sorry, it should be plus 4, so it'll be 5, 2, 1, 6, 3, 0, and minus 1, minus 2, 3. Okay, so let's, in this case, let's swap these two rows, and then we'll scale the top one by minus 1, so we'll get 1, 2, minus 3, minus row 1. Okay, 1, 2, minus 3, 6, 3, 0, 5, 2, 1. Okay, and then we can take minus 5 row 1 plus row 3 and minus 6 row 1 plus row 2 to obtain 1, 2, minus 3, 0, minus 9, 18, and 0, minus 8, and positive 16. Okay, and obviously when you take minus 1 over 9 and minus 1 over 8 but times each of these two rows, this gives us 1, 2, minus 3, 0, 1, minus 2, 0, 1, minus 2. Now we can add row 2 to row 3, which is going to cancel, and we can add minus 2 row 2 to row 1, and we obtain 1, 0, 1, 0, 1, minus 2, 0, 0, 0, which means that x1 plus x3 equals 0, and x2 minus 2x3 equals 0. And so we get that if x3 equals 1, then x1 equals minus 1, and x2 equals 2. And so our v3 is equal to minus 1, 2, 1. So we have so far obtained that D, our diagonal matrix, is the matrix of eigenvalues, which are 0, 3, and minus 4. And P, the matrix of eigenvectors, is given by first eigenvector in the first column, minus 1, minus 6, 13. Second eigenvalue in the second column, minus 2, minus 3, 2. And third eigenvalue in the third column, minus 1, 2, 1. Okay, so the next step is to compute P inverse. And there's not really too many fancy tricks here because we don't have 2 by 2, so we have to just do the row reduction method of finding an inverse. So we start with P in the left-hand side of our 3 by 6 matrix. And we take the identity in the other half. Okay, and we're going to take minus of the first row. Get 1, 2, 1, minus 1. Then this will stay, the rest of the matrix stays the same, minus 6, minus 3, 2, 0, 1, 13, 2, 1, 0, 0, 1. Okay, and there are zeros above here as well, of course. Now we're going to add 6 row 1 to row 2, and minus 13 row 1 to row 3. And that gives us 1, 2, 1, minus 1, 0, 0. So 6 minus 6 is 0. And 12 minus 3 is 9. 6 plus 2 is 8. Minus 6 goes here. 1 is here, and this remains 0. And then we have 0 over here. 2 times minus 13 is minus 26, plus 2 is minus 24. Then we have minus 13 plus 1 is minus 12. And positive 13 goes here, and we have 0, 1. Okay, now we'll multiply row 2 by 1 over 9, and we get much the same matrix. Except our middle row has changed. So we're looking at 1, 8 over 9, minus 6 over 9 becomes minus 2/3, and 1 over 9. Okay. And the next thing to do will be to add minus 2 of row 2 to row 1, and 24 of row 2 to row 3. Okay. And borrowing that for a moment, okay, we're going to leave this here for a moment while I do the calculation. We get 1, 0. Now minus 16/9 plus 9/9 is minus 7/9. And positive 4/3 minus 1 is 1/3. And we have minus 2 over 9 here, followed by 0. Then this row stays the same, 0, 1, 8 over 9, minus 2/3, 1 over 9, 0. And the last row, we get 0, 0. And now 24 times 8 over 9 is, well, you can cancel a 3, and you get 8 times 8 over 3. So it's 64 over 3 minus 36 over 3. So that's 34 minus 6, or 28 over 3. Over 3. 24 times minus 2/3 is minus 16, plus 13 is minus 3. 24 over 9 is 8 over 3. And this column remains 1. Okay, so that is that. Now I can erase this because we have it on the previous slide. And what's left to do? Now we have to multiply this by 3 over 28. Okay, and we obtain top two rows remain the same, and the third row is 1 minus 9 over 28. And this becomes 8 over 28, which is the same as 2 over 7. And this is 3 over 28. Okay, and now we have to cancel the entries above the 1, so we get minus 8/9 row 3 plus row 2, and 7/9 row 3 plus row 1. And that will give us our lovely identity matrix on the left, and in the right-hand side we get minus 9 over 28 times 7/9 is minus 7 over 28, which is minus 1/4, plus 1/3 is 1/12. 2 over 7 times 7 over 9 is 2 over 9, plus minus 2 over 9 is 0. And 7 over 9 times 3 over 28, we have a cancellation of 3's and 7's, so we get 1/3 times 1 over 4, so that's 1/12. Next row, we get minus 8 over 9 times minus 9 over 28 is positive 8 over 28, which is 2 over 7. Minus 2/3 gives us 6 minus 14 over 21, which is minus 8 over 21. Then we get minus 8 over 9 times 2 over 7 is minus 16 over 63, plus 7 over 63 is minus 9 over 63, which is minus 1 over 7, and minus 8 over 9 times 3 over 28, again we have a cancellation of, this time of 4 and 3, so we get minus 2 over 3 times 1 over 7, which is minus 2 over 21. And then the rest remains the same, so we have minus 9 over 28, 2 over 7, and 3 over 28. And hopefully, the matrix that we've arrived at here is our P inverse. Okay, and then putting that all together, we have that our matrix here, which is A, is equal to P, which we saw is here, and then multiply that by the diagonal matrix, which is 0, 3, minus 4. And then the inverse matrix, which is our P inverse, which gives us this factorization of our matrix as P d P inverse. Okay, and this is our diagonalization. Okay. So let's now take a moment to define diagonalizable. So if A is similar to a diagonal matrix, it is called diagonalizable. In particular, so you can use this diagonalization process with eigenvectors and eigenvalues to get a factorization A equals P d P inverse. Okay, but not all matrices are diagonalizable. In particular, this matrix is not similar to any diagonal matrix. Okay? No way to write it as P d P inverse. The reason for that is it doesn't have two linearly independent eigenvectors. Okay. So now let's suppose we have a diagonal matrix before we get into diagonalization. Suppose we have a diagonal matrix like, as an example, one, two, three. How do we take the 10th power of 1, 2, 3? Well, that's easy because whenever you multiply this diagonal matrix by itself, only the diagonal entry only interacts with itself. So really we're just looking at 1 to the 10th, 2 to the 10th, 3 to the 10th. For most matrices, this isn't true. Okay, so this only works for diagonal matrices. Okay, so in particular, to generalize it, if we have lambda 1 down to lambda n and we raise it to the kth power, that's going to be equal to lambda 1 to the k, up to lambda n to the k. Okay? What about a diagonalizable matrix? So let's say we have some general matrix A. And suppose we can decompose it as P, D, P inverse, where D is diagonal. Okay. Then if I take A to the nth power, that's equal to, I can always just replace PDP inverse instead of A. So that's just PDP inverse repeated n times. N times. But we know about matrix multiplication that it's associative. So I can redraw the parentheses without changing any of the facts here, without ruining the equality. So let's put the parentheses like this. So now we have a lot of groupings of P inverse P, with a single P at the beginning, a P inverse at the end, and then a bunch of Ds. So the P inverse P, recall, is just equal to the identity matrix, so we can forget about it. So this is the same as P D to the N P inverse. Okay? So if you know how to diagonalize your matrix A, you can compute its nth power just by using the diagonalization, right? Take your P and your P inverse, do the easy way of computing a power. So this power is easy to compute. So all you need is P and P inverse, and then D to the N is easy to compute just by taking the nth power of each diagonal entry. Okay, so let's see this in action. So suppose we have this matrix 6, 2, minus 1, 6, minus 1, 2, 3, and we want to take it to the 8th power. Is this a matrix we used earlier? Yes, it is. Okay, so we have a beautiful diagonalization here. Okay, so we're going to borrow that later. Okay, so we have, this is the same as this diagonalization raised to the 8th power, but we know that the P and the P inverse are going to be canceling, so this is just equal to 1, 1, 2, 1, 4, 0, 0, 5 to the 8th power, minus 1, 1, 2, minus 1. And so this 8th power goes inside, so we get okay. And this becomes, well, let's simplify it first using this one. So we get the matrix 4 to the 8th, 5 to the 8th, 2 times 4 to the 8th, 5 to the 8th. Okay, and then multiplying that by minus 1, 1, 2, minus 1, we get, this is equal to 2 times 5 to the 8th minus 4 to the 8th, and 4 to the 8th minus 5 to the 8th. And then it's minus 2 times 4 to the 8th plus 2 times 5 to the 8th. And 2 times 4 to the 8th minus 5 to the 8th. Okay, and that's your answer, without having to do 8 different multiplications of 2 by 2 matrices. Okay, if you want the explicit answer, you just have to plug 5 to the 8th and 4 to the 8th into a calculator. Okay, so that was powers of diagonalizable matrices, and now we're going to see one final application of diagonalizing matrices, and this comes from differential equations. So we'll recall that there's a very nice differential equation of the form y prime equals some constant times y. And there's a very simple solution to this, which you'll recall from calculus, is y will be equal to some constant times e to the 3x. Okay? Because when you take the derivative, you get y prime equals, by the chain rule, 3 times ce to the 3x. Okay? And this accounts for all solutions. And any solution to this differential equation will be of this type. Okay, and of course, more generally, if you have y prime equals lambda y, the solution will be y equals ce to the lambda x. Okay? So what happens if we have a system of linear differential equations of this type? So this is a little harder to work with because nothing is a constant. You don't have anything of the form y prime equals constant times y. Now it's a linear combination of these other things. Well, we're going to try to turn this into something that looks like u prime equals lambda u. Okay, or specifically u1 prime equals lambda u1 and u2 prime equals lambda 2 u2. Okay? And the way we're going to do that is using linear algebra, turning this into a matrix equation and then diagonalizing. So we're going to declare this bold y to be the vector y1, y2, and we're going to let A be the matrix 1, 1, 4, minus 2, and we're going to declare the letter D to be the differentiation operator. Okay, so what we have here is dy equals ay. Okay, and what we want to do, or really, I should put this in the vector form, so it's d times y is a times y. Okay, so if we could diagonalize a, then we could get closer. So diagonalize a to reach a system that looks like this. Okay? So let's continue the problem. So we have, again, it's 114 minus 2. So we're looking at (1, 1, 4 minus 2, and we want to diagonalize this. So let's find eigenvalues and eigenvectors. We take the determinant of a minus lambda I, which is equal to 1 minus lambda, 1, 4, minus 2 minus lambda, which is equal to 1 minus lambda, minus 2 minus lambda, minus 1 times 4, which gives us lambda squared plus 2 lambda minus lambda. So that's plus lambda minus 2 minus 4 is minus 6. Okay, so this factors to lambda plus 3, lambda minus 2. So that means that our eigenvalues are lambda 1 equals negative 3 and lambda 2 equals 2. Okay, and now we need the corresponding eigenvectors. So we get v1, so first plug in lambda 1. So we get 4, 1, 4, 1. So this, if this is equal to 0, that means that 4x1 plus x2 equals 0, which means x2 if we set x1 to be, let's say 1, that means that x2 equals minus 4. Okay, so we have an eigenvector v1 equals 1 minus 4, and lambda 2 equals 2. If we plug that in, we get minus 1, 1, 4, minus 4. Okay, and this gives us that minus x1 plus x2 equals 0, so they're the same, which means that v2 is equal to 1, 1. Okay, so to diagonalize, so we have 1, 1, 4 minus 2. Well, our D is going to be the diagonal matrix with eigenvalues, which is minus 3, 2. Our P is equal to the corresponding eigenvectors, which is 1 minus 4, 1, 1. And now we just need to find P inverse. So we get P inverse equals, so we can use the formula. It's 1 over the determinant, which is 1 minus negative 4 or 5. And then we switch these entries and negate these entries, and we have our inverse. So in summary, we have the derivative of y. I really don't like writing bold. Oh well. Derivative of y equals p dp, or this really should be, I'm going to write a tilde for the differentiation one. P dp inverse times y and we can multiply P inverse on both sides, and this becomes d tilde P inverse y, since d tilde and P inverse commute, but that's too much detail, equals d times P inverse y. So what we see is that the derivative of P inverse y, so if we name a new variable u equals u1, u2 to be equal to P inverse y, then this is now d tilde u equals just this simple diagonal matrix times u, which means that u1 prime equals minus 3u, and u2 prime equals 2u2. And these are easy to solve. We have u1 equals c1 e to the minus 3x, and we have u2 equals c2 e to the 2x. Okay. And now we just need to solve for y. So if u equals P inverse y, that means that y is equal to P u. Okay, so if u is, as we wrote here, well, first let's get P. P was 1 minus 4, 1, 1. And u is c1 e to the minus 3x. And c2, and u2 is c2 e to the 2x. That means that y is equal to c1 e to the minus 3x plus c2 e to the 2x minus 4 c1 e to the minus 3x plus c2 e to the 2x. And these are our two solutions. And if you want to double check, we said, for instance, y1 prime equals y1 plus y2. Check. y1 prime equals y1 plus y2. So what's the derivative of y1? Well, that's minus 3c1 e to the minus 3x plus 2c2 e to the 2x. And is that equal to y1 plus y2? Indeed it is, because you have c1 minus 4c1, so that's minus 3c1 e to the minus 3x plus 2c2 e to the 2x. Check, that works out. And you can check the other equation for yourselves. So to summarize how we approach this problem, you start by having y prime equals ay, where A is a general matrix. Then you diagonalize A to obtain a new differential equation, which is P inverse y prime equals some diagonal matrix applied to P inverse y. Now, because you're using a diagonal matrix, you can solve for P inverse y using just exponential functions. And then you can multiply both sides by P to find your original y. And that's how to use diagonalization to solve differential equations. Thanks so much for your attention. I think I went a bit longer than expected, but it's some interesting material. Have a great day.